deflection, and why should I care? Well, it's something that affects the stability of everything around us, from the buildings we live on to the bridges we drive on. Stick around as we break it all down for you.
Okay, let's start with the basics. Beam deflection is how much a beam flexes or bends when a load is applied.
Imagine this ruler is a beam. When I press down on it, you can see it bends. This bending is deflection, and it happens because beams aren't perfectly rigid. But understanding how much they bend is crucial.
Now, not all materials behave the same way. For example, steel bends less than wood under the same load.
In real-world structures such as bridges, skyscrapers, and homes, deflection is something engineers carefully calculate. Why? Because too much deflection can cause cracks, structural failures, or even collapse.
Engineers use formulas or online calculators to predict deflection like this one. By plugging in factors like the load, materials, and the span, you can predict how much your beam will bend. For example, if you take a steel beam that is 10 meters long and apply 5,000 kilograms of load, calculator will give us a precise value of deflection that we can expect. This helps engineers design structures that are strong enough without wasting materials.
Now, let's look at where beam deflection plays a critical role in real life. Take bridges for example. Without proper calculations, your beam could have too much bending, which could lead to dangerous situations. But if your beam doesn't flex at all, your beam could break from all the strain that is on the beam. So it's a balance between strength and flexibility.
Beam deflection isn't just important in bridges. Look at high-rise buildings. The beams that holds up each floor have to support the weight of the buildings and everything inside, people, furnitures, and even equipments. Even stadium roofs needs to be designed with beam deflection in mind. A roof could collapse under heavy wind or the weight of snow if the beams aren't able to flex properly.
Hey guys, now I'm about to teach you how to solve for flexural rigidity, something that measures the beam's ability to resist bending and is defined by the product of Young's modulus or modulus of elasticity, which represents the stiffness of the material and the moment of inertia. To solve this, you're going to need a calculator, a ruler.
I need my calculator, but I need your help to find it in my backpack.
Backpack.
On the backpack, loaded up with things and knickknacks too. Anything that you might need, I got inside for you. Backpack. Yeah! I have lots of stuff. But Dora needs to find something to help her see in the dark. Will this help Dora see in the dark? Will this help Dora see in the dark? Will this help Dora see in the dark? It will? A flashlight will help Dora see in the dark. You're good at this. Yum. Delicioso!
Ruler or measuring tape, and lastly, a pencil and paper. However, for the purposes of recording this discussion, I'll be doing everything digitally. So, let's dive in. First, you have this beam over here, supported by a pin support on the left and a roller support on the right. It's 8 meters long and is shown to have 2 forces acting on top of it. Each point where forces is acted on top of it is marked, and for this case, there are 4 forces. At P, there is 75 kilonewtons acting downward, and at C, there is 50 kilonewtons. For this example, we'll be solving for the equations of the angular deflection, which is represented by EI theta, as well as the equations for flexural rigidity, which is represented by EI times the vertical deflection. It's also important to determine early on the boundary conditions on the left and the right of the beam. For the left, x and y has no value, so x equals 0 and y equals 0. For the right, we simply have to find the total length of the beam, which is 8. So x equals 8 and y remains the same, so y equals 0. To start, we first have to solve for the reactions on the left and the right support. First, we'll start on the right support, which is dy. solve for dy, we have to make a clockwise moment at point A. This then equates all the forces except A and measures the distance of each force from A. So dy's force travels counterclockwise to A, which means it's negative in terms of that. Its distance is 3 plus 3 plus 2, which is 8. For the 50 kN on point C, it travels clockwise, so it's positive. Its distance is 3 plus 3, so 6. For the 75 kilonewtons on point B, it also travels clockwise, so positive 75. Its distance is simply 3. For the calculator, you simply have to replace dy with x. So it's negative x 8 plus 50 times 6 plus 75 times 3. To automatically solve for x, you simply have to press shift and then solve. A while ago, I forgot to put the plus sign before the 75, so please always remember to do that. With that, we've now found the value for dy, which is 65.625. Next, we can now do the same to solve for the reactions at the left support. We can now make a clockwise moment at D. The force at AY travels clockwise to D, making it positive. The distance is 3 plus 3 plus 3, so it's 8. AY times 8. 75 kilonewtons at B travels counterclockwise and is 5 meters away from D, so it's negative 75 times 5. Lastly, 50 kilonewtons at point C also travels counterclockwise and is 2 meters away, so it's negative 50 times 2. With that, you can now equate it to 0 and input the equation on your calculator. Do the same thing a while ago with replacing AY with x, and also using shift solve to automatically solve for x. With that, we now have our value for AY, which is 59.375. After you solve for your reactions, we can now segment at point CD and draw our full body diagram at segment CD. To do this, we first have to section between point C and D, and then copy all of the forces that are acted upon on the left side of the section. This is just me making the full body diagram. And also don't forget to put the values we found for AY and DY on the actual full body diagram. For the distances, we can assume that the section's full length from the moment of CD on the right to AY is x. For each succeeding distance, we just have to subtract the distance it loses as it gets closer to the moment of CD. So for the force of 75 kilonewtons, it's x minus 3, and for 50 kilonewtons, it's x minus 6. And here I am reflecting the values for DY and AY. Next, we have to solve for the moment at segment CD. So to do this, we first have to equate moment CD to 0. By using our new full body diagram at segment CD, we can do what we just did a while ago and multiply the distance with each corresponding force from moment CD, and use their direction of rotation as a basis for their sign. With our moment at segment CD made, we can then now make our working equation, which is EI double prime equals M. To do this, we simply have to copy the equation that we made for moment at segment CD. Replacing parentheses with brackets, make sure that the effect of a force or load only starts at a certain point and doesn't affect anything else before that. It's a way to handle things like when you press down on a beam at a specific spot only. And that's why we use brackets on some of the terms. Start with 59.375 times x. To integrate this, remember that integrating x gives us x squared, and we divide by 2. Next, we look at negative 75 times the bracket of x minus 3. When we integrate this, treat the bracket of x minus 3 like x by itself but shifted. So we square the bracket and divide by 2. This gives us 75 times the square of the bracket of x minus 3 over 2. Don't forget to put the power of 2 over x minus 3. Now for the final part, negative 50 times the bracket of x minus 5, we do the same thing as the previous step. We square the bracket of x minus 5 and divide by 2. This results in negative 50 times the square of the bracket of x minus 5 over 2. Now for the second integral, for the first part, 59.375 times x squared divided by 2, we integrated. This becomes 29.6875 times x cubed over 3. Next, look at minus 75 times the bracket of x minus 3 squared divided by 2. When we integrate this, it becomes minus 37.5 times the bracket of x minus 3 cubed over 3. Now for the final part, minus 50 times the bracket of x minus 6 squared divided by 2. When we integrate this, it becomes minus 25 times the bracket of x minus 6 cubed over 3. Now let's put all of it together. The final integrated expression is 29.6875 times x cubed over 3 minus 37.5 times the bracket of x minus 3 cubed over 3 minus 25 times the bracket of x minus 6 cubed over 3 plus c1, where c is the constant of integration. With our two equations and by using the boundary conditions we've determined a while ago for the left support, we can now solve for c2. A while ago, I forgot to put the constants on the first integral as well as the second integral. Here it's shown when it's already put in. Now to solve for c2, all we have to do is substitute the boundary conditions at the left support and substitute it to the second integral. With this, we get EI0 equals to 29.6875 times 0 cubed minus 37.5 times the bracket of 0 minus 3 cubed over 3 minus 25 times the bracket of 0 minus 6 cubed over 3 plus C1 times 0 plus C2. No need to put this in your calculator as it simply equates to 0. Moving on to solving for C1. We will still be using the second equation, and instead of boundary conditions at the left, we'll be using the ones on the right, which is x equals 8 and y equals 0. After substituting, we get EI0 equals to 29.6875 times 8 cubed over 3 minus 37.5 times the bracket of 8 minus 3 cubed over 3 minus 25 times the bracket of 8 minus 6 cubed over 3 plus c times 8. After inputting in your calculator and substituting C1 with x, you'll get negative 330.3376. With all of that solved, you can finally get the equations for angular deflection and flexure rigidity multiplied by the vertical deflection. For the equation of the angular deflection, you simply have to use our first equation, which is the first integral equation, and substitute our value for C1. This gives us 59.375 times x squared over 2 minus 75 times the bracket of x minus 3 squared over 2 minus 50 times the bracket of x minus 6 squared over 2 minus 330.338. Now, for the equation of the flexure rigidity multiplied by the vertical deflection, we'll simply be using the second equation, which is the second integral, and substituting our values for C1 and C2. After putting it all together, we get 29.6875 times x cubed over 3 minus 37.5 times the bracket of x minus 3 cubed over 3 minus 25 times the bracket of x minus 6 cubed over 3 minus 330.338, and we won't be including C2 as it equates to 0.
Deflection isn't only a concern for larger structures. Even for smaller projects like building a deck for your home or building a bookshelf, deflection matters.
So the next time you walk across a bridge, drive down a highway, or spend time in tall buildings, remember that beam deflection is always at work, quietly keeping everything safe and sound.
So thank you for joining us today. We hope you learned something new about the importance of beam deflection in engineering.
If you found this video helpful, don't forget to like, comment, subscribe, and hit that notification bell for more